Welcome to the 7th and final section of our unit on geometric optics. This unit is going to again focus on thin lenses, specifically on doing calculations of where the images occur and characterizing the images based off of the calculations. First, a reminder of what we saw in the last unit. Convex lenses can produce 3 different types of images depending on where the object is. So if the object is out past 2f, so is 2 focal lengths away from the center of the lens, then the image will be real, inverted, and diminished. If the object is between 2f and f, then the image is real, inverted, and enlarged. And if the object is between the lens and the focal point, then the image will be virtual, upright, and enlarged. Concave lenses, on the other hand, can only produce one type of image, and that image will be virtual, upright, and diminished. The thin lens equations and magnification should look very familiar to you because they're the exact same formulas that we encountered with the spherical mirrors. So the focal length is related to the object distance and the image distance through 1 over the focal length is 1 over the object distance plus 1 over the image distance. Now you may be wondering and thinking about it because lenses have 2 focal points. So if I think about my lens, I've got f2 on this side and f1 on that side for a convex lens. And if drawn properly, then the distance from the center of the lens to f1 should equal the distance from the center of the lens to f2 because both are 1 focal length away from the center of the lens. The magnification formula is also identical to what we had before. So the magnification is the negative of the image distance divided by the object distance. Or you can find it by taking the ratio of the image height to the object height. One other piece that you need to know is that for lenses, we have a parameter called lens power. And by definition, the lens power is 1 over the focal length of the lens. If the focal length is measured in meters, then the lens power is given in diopters. When you go to the optometrist and get a prescription, your prescription is in units of diopters. Okay? If you think about this, as the focal length gets smaller, meaning that the light changes direction more quickly, and therefore the lens is changing the direction of the light more quickly, that implies that the power of the lens is bigger. It's having to make a bigger change. It's having to do more for your eye. As with mirrors, if you're going to use these equations with lenses, you have to have the lens signs conventions. Okay, so a positive lens is a convex lens. Remember, convex lenses had 3 different names. They were positive, they were convex, or they were converging. The reason they're called converging is because they can cause light to come to a focus. I can use a magnifying glass to focus light down to a point. Okay. Concave lenses, remember, also had 3 names. They were concave, they were diverging, and they were negative. The positive and negative distinction comes from the sign convention for the focal length. Objects that are in front of the lens are going to be real and positive. Objects behind the lens will have a negative DO and are virtual. However, to get a virtual object, you have to have more than one optic. Therefore, you're not going to encounter them in this class. We're not doing systems of optics, so you don't really need to worry about that one. Okay. Images that are behind the lens are real and will have a positive image distance. If the image is in front of the lens, then it will be virtual and will have a negative image distance. Image height and magnification is again positive for upright images and negative for inverted images. For our first calculation, we're going to work with a concave lens. The object distance is 20 centimeters, the focal length is -5 centimeters, and the object height is 0.5 centimeters. As with mirrors, our goal here is to not only calculate all the things we don't know, but it is also to look at the results of our calculations and characterize the image. Okay, so the first thing we're going to do is we're going to find the object distance using the relationship between the focal length, object distance, and image distance. Okay. Plugging in 1 over negative 5 centimeters equals 1 over 20 centimeters plus 1 over di, which means 1 over di equals negative 1 over 5 centimeters minus 1 over 20 centimeters. Remember to find a common denominator here. So that's negative 4 over 20 centimeters minus 1 over 20 centimeters, or negative 5 over 20 centimeters, and that equals 1 over di, which means di is the reverse of that, or 20 centimeters divided by 5 with a negative sign out in front, which is negative 4 centimeters. I can look at this and I say, hey, it's negative. That tells me it is virtual. I can now find the magnification using the negative ratio of image distance to object distance. The image distance we just found at negative 4 centimeters. The object distance was given as 20 centimeters. So 4 divided by 20 is 1/5, and those two negative signs cancel each other out. Remember, the magnification does not have a unit. Here I can see that the magnification is positive, which tells me it is upright. And I can see the absolute value of the magnification is less than 1, which tells me it is diminished. Okay. Finally, I can use the other definition of the magnification to find the image height. So the image height is going to be the magnification multiplied by the object height, which is 1/5 multiplied by 0.5 centimeters, or 0.1 centimeters. I can now look and see that HI is positive. That tells me it is upright. And if I compare HI to HO, again, absolute valuing, because occasionally these things can be negative, I see HI is less than HO, which tells me it is diminished. Diminished. Can't spell right now. Okay. If I go back a couple of slides and look, too far, I see that a concave lens can only give me a virtual upright diminished image, which is consistent with what I just got from my calculations. This is a virtual upright diminished image. Now, a similar calculation for a convex lens. So 1 over the focal length is 1 over the object distance plus 1 over the image distance. In this case, our object distance is 7 centimeters, the focal length is 5 centimeters, and the object height is 0.5 centimeters. So I can plug in that F is 5 centimeters, DO is 7 centimeters. If I now rearrange, 1 over DI is 1 over 5 centimeters minus 1 over 7 centimeters. Now you could find a common denominator here, or you can just put this into a calculator and you would find 1 divided by 5 plus 1 divided by 7. Oh, I forgot to subtract. Let's try again. 1 divided by 5 minus 1 divided by 7. This gives you a value for di. 1 over di equals 0.057 with units of 1 over centimeters. So to find di, I have to take the inverse of this, which gives me di is 17.5 centimeters. And look, it is positive. Therefore, it is real. I can now find the magnification by taking the ratio of the object distance or the image distance to the object distance with a negative out in front. So that's negative 17.5 centimeters divided by 7 centimeters. So 17.5 divided by 7 is 2.5 with a negative sign because that comes along for the ride. And now I see m is negative. That tells me my image is inverted. So if I were to image a tree, the tree would look like its roots are in the sky and the leaves are heading towards the ground. It's upside down. I also see that the absolute value of m is greater than 1. Therefore, this is going to be a magnified or enlarged image. I can now use the other definition of the magnification to find the image height. So the image height will equal the magnification multiplied by the object height, which is negative 2.5 centimeters times 0.5 centimeters, which is negative 1.25 centimeters. Oh, and I put units on my magnification when I shouldn't, all the way through. So please remember the magnification is unitless. Get rid of those. Now I can see that the image height is negative. That again tells me it is inverted. And I see that the absolute value of the magnification is, oh, I'm on magnification. Let's try not that. We've already done that. Let's compare the image height to the object height. And I see that the absolute value of the image height is greater than the object height. That again tells me I am magnified. Okay, now let's come up here really quick. I see that f is 5 centimeters and 2f would be 10 centimeters. And my object is right in between those. Okay. Going back to here, when the object for a convex lens is between 2f and f, I get a real, inverted, enlarged, or magnified image, which is exactly what I saw here. It is real, it is inverted, and it is magnified. Now, what we have between spherical mirrors and thin lenses is two sets of images and two sets of sign conventions that are very similar but not the same and just different enough that they can be confusing. So I'm going to take two slides here to try to put things into a perspective where you can only have to think about one set of sign conventions and only have to think about one set of images, if that makes sense. Okay. So first off, I'm going to think about my convex lens or my concave mirror. Both of these, the convex lens and the concave mirror, are able to focus light to a spot. Okay. Okay. The concave lens or the convex mirror cannot do that on its own. Okay. Both of them, the convex lens and the concave mirror, can produce three types of images, again depending on where the object is relative to f and 2f. But remember, for a mirror, this wasn't written in terms of 2f. It was written in terms of RC. But remember, RC is by definition at 2f. So it's really the same boundary point. Okay. So if the object for the convex lens or the concave mirror is out past 2f, the image is real, inverted, and diminished. If the object is between 2f and f, the image is real, inverted, and enlarged. And if the object is between the center of the object and the focal point, then the image will be virtual, upright, and enlarged. The concave lens or the convex mirror are only capable of producing one type of image. It will always be virtual, upright, and diminished. Okay. Similarly, for the sign conventions, the optics that are capable of focusing light to a spot both had positive focal lengths. The other ones, and I see I have a typo here. Instead of convex, it should be convex. The concave lens and the convex mirror were not capable of focusing light to a spot, and both of those had the negative focal length. Real objects had positive DOs. Virtual objects would have negative DOs if we would use them in this class. Real images always had positive DIs. Okay. Remember, real image for a lens is behind the lens because lenses are designed to refract light through the lens, whereas mirrors are designed to reflect. Therefore, a real image for a mirror is on the same side as the object. Okay. Similarly, all virtual images had negative values of DIs. And for both sets of optics, this did not change. Image height and magnification was always positive for upright images and always negative for inverted images. I hope this effort to try to bring the two into agreement, so you only have one set of sign conventions to use and remember, helps you. This concludes our unit on geometric optics.